Hello everyone and welcome to the 53rd lecture of the course Advanced Structural Analysis. We have discussed the P delta effect in the last session and we looked into a simple iterative scheme which can analyze the general response of the system when the P delta effects are considered. To be more specific, P delta effects in general when we consider for general design which are included in the software modules. So, we not only do it with a calculation of the general iterative part, but the system also considers the inclusion of the geometrical stiffness. So, as a next part of the system we will try to see that how the simplified iterative scheme which we already discussed can be extended to the geometrical stiffness based approach, and then the overall solution which we obtain from the given system. As we realize that the moment we have a geometrical stiffness in the given system, that means the nonlinearity has been added, and now the solution of the system may not be a very specific solution which we get through the inverse of the stiffness matrix. In these cases again we have to go to the standard nonlinear equation solvers like Newton-Raphson, and that we will try to see now for a multi degree of freedom system. But at the same time we also realize that all these computations are not possible with the manual calculations. So, one has to go to the computing system when one is doing these all calculations in the given system. We have already done the discussions on the formulation of the stiffness approach, the general extension of the regular stiffness approach to the computing system, and with the previous set of assignments and the problems, you must all be much more comfortable to use the regular computer codes to solve the system of general structural framework for any kind of the regular static loads on the given system. Now, if we add on that the contributions of the geometrical stiffness, and we are also able to identify the procedure to add the P delta contributions, we will be able to comprehensively transfer the same codes to the regular nonlinear analysis procedures. Okay. So, with that the given content is prepared, we will go with the conceptual discussion that how the overall process is implemented. I will try to show in the each of the steps that how the procedure is done, but it will not be possible to show in the classroom that how does the typical example of the given system is done, because that typically require the full computing code to be run on the given system. So, we have already shared the earlier computer codes with you, but any one of you if like willing to go through the nonlinear geometrical stiffness related assignments or the specific part of problems, so we can also be happy to share these codes to identify that this is the system which we want to solve with the P delta analysis, considering the geometrical nonlinearities in the given system as well. Now, I am going with the procedure in a manner such that the overall approach can be extended to the system of the same stiffness method which we did earlier in the system. So, as a first step of analysis, we consider that we have to have the stiffness matrix K of the given system, or I will say that the linear stiffness of the given system. I need to define the linear stiffness of the given system. As I realize the given system that I have individual members identified, I can define first for each of the member the stiffness matrix, and then I can convert these stiffness matrices to the by the node connectivity to the overall global assembly of the given system. So, the stiffness matrix for the overall system or the global system can be defined by evaluating the individual element stiffness matrices for each of the system. At the same time, the application of the linear stiffness which we do and the way we extend it to the global system, same way I can also do it for the nonlinear as well as the geometrical stiffnesses of the given system. So, any amount of the stiffness which we define at a member level. So, if you recall the discussions which we did for the geometrical stiffness of the beam members, I considered that at the local member coordinate we have 3 possible degrees of freedom, which are u1, v1 and theta 1 at one of the node, u2, v2 and theta 2 at the node 2. Now, with respect to this given system, we were able to identify the linear as well as the nonlinear stiffness of the given system, and additionally with that we were also able to identify the geometrical stiffness of the given system. We call that total system as the KT, which is the tangent stiffness of the given system. This tangent stiffness was identified as a 6 cross stiffness in the local member coordinates. I can do the transformation of this KT matrix and convert the given KT for individual member I in the global system. So, this is again the same 6 cross 6 matrix, but it is defined in the global system. Once the transformation is done and the system stiffness in the global coordinates has been obtained, the user can go with the node connectivity system and generate the overall global assembly of the system, which is now for the KT, and I call it as a global. And if we have, say, the total n degrees of freedom in the given system, the size of this matrix will become n cross n in the given problem. So, with this idea we are able to identify a simplistic procedure in which the KT as a tangent stiffness matrix can be evaluated. What you need other than the regular linear stiffness which was done in the previous problems is the only contribution of the nonlinear and the geometrical stiffness terms of the given system. But only to be little careful about that these terms of the nonlinear and the geometrical stiffness parameters are not going to be the constant values, but rather they are itself function of the displacement terms. So, assembly of them as well as general derivation of them require some additional steps in the given system, which we discussed in the previous lectures. Now, using this idea I will try to show that how do we proceed with the given problem. So, the idea is that we have already known that what is the linear, nonlinear and the geometrical stiffness of the given system. In fact, we have also made a point that for the regular P delta analysis, a user can also reduce the nonlinear term which is coming due to the large displacement and only add the geometrical nonlinear term in the system, which is actually due to any kind of a compressive forces in the given member, right. So, these are now kind of some simplifications which we make in the given simulations or the given problems, so that the analysis of the system can be done in a more realistic and a faster way. Why it also becomes much more important, because if you think about the general structural system which are having say thousands or more than that components, using the methods like matrix analysis or say even a finite element analysis, the systems can go with the degrees of freedom which will be in the lakhs. Now, using the stiffness calculations with the degrees of freedom up to lakh or maybe more than that could be very computationally expensive. So, if we make a modification which can reduce the computational steps, that could make very much significant changes in the overall simulation time. And in that approach we have come up with some very simplistic ideas. One is that we do not need to consider the nonlinear stiffness contribution due to the large displacement, because in a simplistic frame like systems I can consider that yes, the sway in general which is available in the system and the compressive loads which are active in the given system, they can all be calculated or accommodated in the Kg matrix of the given system. But other than that I do not need to generally include the nonlinear terms of the given stiffness contribution in the given system. One more simplification which the user can make is that mostly it is the columns which are subjected to the compressive loads. So, when we go with the calculation of the geometrical stiffness matrix, I can concentrate only on the contributions of the geometrical stiffness matrix coming from the columns of the given system. I can leave my beams without the contribution of the geometrical stiffness, because they are most of the situations not subjected to any kind of in plane compressive loads of the given system. So, with this idea the overall procedure of the given analysis can be simplified, and that becomes much more faster also in the software systems as well as in the computer codes. Now, with this part we realize that we label the given numbers. Now, the procedure is very similar to what we did in the previous sessions. So, we identify all the nodes of the given system, we label the given nodes of the members of also of the given system. Based upon that, for each of the node number we will be identifying that what are its x and y coordinate, whether the system is restrained or not, and also we will identify for each of the member what are its the two end joints j and k of the given system, the member area as well as the elastic properties, the second moment of area, the length as well as the orientation related properties of the given system. So, once we identify all these input parameters of the given system, we are now in a position to identify the stiffness of the given problem. To define the stiffness, we already know that the general stiffness for a regular frame member contains the 6 cross 6 stiffness contribution for a plane frame, and these contributions have been identified in this manner. Now, these contributions are defined in the local coordinates. As I already said that we first calculate the values in the local coordinate of the given system, and this is, to be very careful, this is only the linear term of the given system. So, I am going with the analysis where I am only taking the linear terms and the geometrical stiffness term of the given system. I am not adding the nonlinear stiffness term of the given system, which is due to the large displacement. But in case if you want to take it, the procedure will remain similar to what we have done over here. So, I define the stiffness of the given system, I take the general transformation matrix of the given system with these two rotation tensors or the rotation matrices which have been defined on the given system, and we convert our local member coordinate stiffness matrix to the global stiffness matrix of the given member. So, the given stiffness matrix is still a 6x6 stiffness matrix defined for the member I, but only thing it is defined in the global coordinates of the given system, which are in the global xyz directions or xy theta directions of the given system. Once we have the stiffness for the given individual member, we can do the same thing for individual member for the geometrical stiffness in the given system. Now, how do we obtain the geometrical stiffness? If you recall the discussion from the beam member, we have any of the member I corresponding to which we define these degrees of freedom, say u1 v1 theta 1, u2 v2 theta 2, and we get this 6x6 stiffness matrix of the given system. Now, those of you who have not seen this part of the system earlier, I will just ask that once you can just have a look at the stiffness expression, the geometrical stiffness expression which we derived in the last week. In the week 9 we have done, week 10 we have done this derivation where we evaluated the stiffness, geometrical stiffness for the beam like members, and that we define in terms of the individual shape functions n3, n4, n5 and n6 of the given system. We have given the values of these shape functions also in the given system, and based upon that we are able to now evaluate the stiffness matrix of the given system. Now, this stiffness matrix is again defined in the local coordinates, and once I have got the stiffness matrix for the member I in the local coordinate, I can utilize the same transformation rule and convert the stiffness matrix in the global coordinates of the given system. So, this is the stiffness matrix which is still defined for a given member I, but that is defined now in the global coordinates, and it still has a size of 6x6 in the given system. Now, once we have defined these values, I can go with the assembly of the given system. So, we assemble the overall stiffness matrix of the system. I think we can now go back to the same discussion which we did in the general stiffness formulation. We define the individual nodes of the given each of the member and locate that where the stiffness for that particular member will go in the global system. So, just to make a one idea in a simplistic manner, this system has total 6 number of nodes in the given problem. So, I will realize that the given system will have 3 into n, which is 18 number of total degrees of freedom in the given system. That means, the overall size of the stiffness matrix of the given system or the geometrical stiffness of the given system will be defined as 18 cross 18 in the given problem. Now, in this 18 cross 18 matrix, where the individual members will contribute, because you have got the calculations for each of the member for their geometrical for their linear as well as the geometrical stiffness of the given system. So, once we have the geometrical and the linear stiffness for each of the member, we can apply the individual contributions in the given k and kg matrices of the given system by considering that for any of the member which we located over here, say ith member, for which the joint j and k are defined, the individual degrees of freedom which the given system will entertain will be located as 3j minus 2, 3j minus 1 and 3j, whereas this one 3k minus 2, 3k minus 1 and 3k in the given system. So, I think this is what we have done already in the previous system. So, I can now make a vector containing these 6 degrees of freedom positions of the system, and I can specify that individual member, say the stiffness, linear stiffness for the member I, which is already defined in the global coordinate, that will be going to the specific position of these particular degrees of freedom in the overall k matrix of the system. Similarly, I can come up with the geometrical stiffness matrix for the member I, and I will put that stiffness matrix in the position of these degrees of freedom in the k of g, the global stiffness matrix of the geometrical stiffness in the given system. So, once I am able to do this kind of the procedure, I will be able to get the overall stiffness matrix, the linear stiffness contribution of the system, as well as the geometrical stiffness contribution of the given system. But we now realize that the geometrical stiffness which you see over here is coming as a function of S of x, where S of x happens to be the member force active in the given system. So, these are the compressive forces which are active in the given system. As I already said that if you have a beam member, you can simply say that the beam member does not have any compressive force, so the S of x is 0. So, that means the overall kg contribution for the beam member becomes 0, right. So, with these ideas in mind, I can now assemble the overall stiffness matrix, and I realize that the geometrical stiffness is a function of S of x. Now, also to be very careful about it, the S of x, which is not a single value, because there may be multiple columns and they may have their own individual member compressive loads in the given system. So, while you are defining the individual geometrical stiffness matrix for any of the member I, the S of x component will also be individually defined. So, that could be common across all the members, as well as that could be a member component which is updating or which is changing its value from each member to member. A very simplistic example, if I consider that, say this is a particular frame system, I simply go with say just a 2-story frame. Say over here there is a load of say 200 kilonewton, and at this point say that due to some other part of the work of the given column, or say someone started contributing with the other some of the components of the load, started adding the load over here, and that comes out as say 300 kilonewton on the given system. So, when I go with the calculation for the story 2 column, I will be coming with the compressive load of 200 kilonewton, whereas when I will be going with the bottom story contribution, I have to define the compressive load of the 300 kilonewton. So, accordingly the value of S of x will be different for the bottom column and the first story column of the given system, and that need to be contributed in the general framework as well, right. So, now with this idea we have a equation in which the stiffness matrix, the geometrical stiffness matrix are known to us, delta is not known to us, and the force can be defined based upon that what are the external loads identified in the given problem. Now, the question comes that how do we solve this multi degree of freedom system, because now we have not one degree of freedom, but there are more than one. There could be one easier way in which say the member forces are constant. This is what we did in the previous case, where we simply kept on updating the given system by considering that the member force does not change, which means that you had a column and even the system has undergone some deformation, the member force remains same, which is defined as the initial value of 500 kilonewton. But in many of these situations, if this is the situation, then the problem becomes much more easier. We go with the K calculation, which is a linear stiffness. We go with the K of G, which is with respect to a constant value of S of x. So, it will also become a constant value. Now, you have delta, which is unknown, force value is known to us. So, you can evaluate the value of the force. Now, as a next step, one has to go with the iterations to calculate whether the effect of this force, which is active on the given compression member or the column, with respect to the given lateral drift, is included as an additional moment on the given system, and will that affect the overall analysis in the given system or not. So, this is one easier way to implement the system, which is again like a iterative method, where the S of x is constant, but we are able to evaluate the response of the system with respect to the iterative scheme in the given problem. The second approach, in which the member axial force is not constant and is being updated at a instance with respect to the change in the displacement, becomes more critical. So, we say that now the force in the member, say S of x, is also the function of the displacement, which means that like the truss members we consider, that we have some of the displacements which are taking place in the member. Say if I just define in the local member coordinates. So, if these are the displacements u1 v1, u2 v2. So, accordingly I can calculate that what will be the change in the length of the given member, which is say u2 minus u1 in the given system, and according to this value of the deformation in the member length, I can calculate that what will be the force in the given system. So, I can calculate that the force in the given system S will be equal to AE upon L, where the value of the change in the length, which is the u2 minus u1, is also defined. So, I will say that this value is E. So, AE upon L into E, that becomes the individual member force in the given system. So, in any of the situations where these value of u1 and u2 are continuously changing as the nonlinear analysis is being done, the value of the member force S of x will also keep on updating itself, and that is where the nonlinearity is introduced in the given problem. So, as a next case, we will try to see that once you have formulated an equation like this, and now the forces are changing and they are updating itself at each of the instance, how do we take care of it? Okay. So, this problem I will try to see it from the perspective of the truss members, because there it becomes more evident in terms of the updated force of the given system. So, we go with the same previous problem which we have done, but rather than now considering the general symmetric case which we did earlier, I have now added the load P1 which is in the direction of the vertical symmetry direction. Now, I have also added another load which is P2. Now, this load will break the symmetry of the given system, and that is why I have to now go with a full scale analysis for the given problem. So, just to consider that what does this full scale analysis means, I can consider that the system has these 3 nodes. At each of the node it has 2 degrees of freedom, say u1 v1, u2 v2, and over here u3 v3 in the given system. So, the stiffness matrix, the tangent stiffness matrix which I am going to define for the given system should ideally be defined as a 6 cross 6 matrix for the overall system. Individually for each of the member also I can define the matrix, and for each of the member, if you recall the discussions which we did earlier in the local coordinates, we define the KT matrix as a 4 cross 4 matrix of the given system. So, from this 4 cross 4 matrix for each member, I need to now convert the assembly. So, first we need to do the transformation on this, convert this KT matrix for the element I in the global directions, and once we have got the global stiffness for the given member I, we assemble for all the remaining members and get it as a total KT matrix for the global system, and that comes out as a 6 cross 6 matrix of the given system. But at the same time I realize that when I will use the solution, that this KT into the delta which is say u1 u2 up to u6 is equal to the force representation of the given system. So, force representation corresponding to the ends I do not know, these are the unknown values. So, these will be denoted as AR1, AR2, AR3, AR4, and corresponding to the values which are over here, I will define the values as P of 2 and this value as minus of P of 1. I think what we will do better, we will keep this as P of 2 and this as a P of 1, so that we can keep it in the same order. So, accordingly this becomes as P of 1 and this becomes minus of P of 2. Now, with this idea, now I have obtained the given system, and we define that as the displacement corresponding to u1, u2, u3 and u4 are all 0. So, I do not need to go with this full 6 cross 6 matrix of the given system, rather I need to only concentrate upon the contribution with respect to u5 and u6, and that will be easily done with respect to this given part of the system, which is a simple 2 cross 2 matrix of the given system. So, I can consider that this 2 cross 2 matrix into u5 into u6 is equal to p1 into p2, p1 and p2, and that can be easily defined as the general solution scheme for the given problem. So, we will try to see these part in the subsequent slides. So, as a first step, we got to know that the KT value, which is the tangent stiffness matrix of the given system, this is for any one of the member. As I said that it is a 4 cross 4 matrix, contains the linear part, the non-linear part due to the deformations, and the geometrical non-linear part of the given system. This part for now I am not considering that the displacements, large displacements are included only with respect to the geometrical stiffness term of the given system. Now, the next part, we add the K plus Kg with respect to the overall system as I contributed, and that comes out as with respect to all the degrees of freedom into the forces of the given system. Now, what we have done, the individual Kg, as I already said, will be coming out as a function of the forces, the member forces in the two components or the two members of the system. So, if we look at the KT expression, KT comes out as a function of the member force. Now, when you go with the member 1, the force is say S of 1, and when you go with the member 2, say the force, so this is say the member 1, this is member 2, and in this the compressive force is say S1, in this say the force is S2 in the given system. So, accordingly the Kg will come out as a function of S1 and S2 in the given system. And now what we realize that S1 and S2 are not constant values, but they are also updating themselves with the changes in the displacement values of the given system. And we have very well seen this, that as the displacement value changes in the given system, like these displacement values, the internal force of the member can also be modified. Now, with this idea in mind, I can come up with the calculation that this is the simplistic matrix, which is the sub part of the given system with only u3 and v3 components, equal to p1 and minus p2, and this is the contribution of a simple 2 cross 2 part of the stiffness matrix of the given system. This 2 cross 2 matrix part is identified from this position of the given global matrix. Now, once I am able to solve this given problem, I will be getting the solution of the overall problem. So, the question arises that how do we solve this given problem in which the forces S1 and S2 are updating themselves at each instance of the time. So, to start with, what we consider, we initially consider that when the system is having no displacement, say all the values of the displacement u3 and v3 are also 0, we consider that what will be the forces in the given system, say S1 and S2. We evaluate the force values, say the initial values. So, these are the values, most likely they will also come out to be 0, and with respect to these values, once we have the given system, I evaluate the overall stiffness matrix of the given system, which is K plus Kg in the given system. So, knowing the initial values of the forces, we can evaluate the stiffness matrix of the given system and do the simple linear analysis, because now the K value has come out as a constant value, and I can calculate the value of u of 3 and v of 3 in the given system. Now, this is very similar to what we do in the Newton-Raphson method. In fact, this is the Newton-Raphson for the multi-degree of freedom system. I obtain the first value of u3 and v3 in the given system by considering the value of the K plus Kg with respect to the initial values being 0 in the given system. Now, once we have got these values, I realize that corresponding to this u3 and v3 values, the internal member forces S1 and S2 are not constant, they are not the 0 values. So, as a next step, I again re-evaluate the member forces in the given system. Now, they come out with the different values, say S1 and S2. We also obtain the values of P1 and P2 as per the initially defined values of the given system. But what we also realize that once we substitute the value of the updated stiffness parameter or the updated member force in the given system and substitute over here in this K plus Kg term, the value of the forces come out different than the loads which have been applied on the given system. So, this is same problem which we faced earlier in the Newton-Raphson scheme also, and that is where now we start with the modification or the going with the iterations in each of the increment of the given system. So, to look at this process more in a broader manner, we come up with the first part. We go with the step 1, we say that define the u3 and v3 the initial values. Once the initial values are defined, say we take the values as 0 and 0, we get the initial values of the S1 and S2. Based upon these values of the S1 and S2, we define the K of G, which will come out now as a constant value of the stiffness matrix. Now, solve the given system for this initial value and obtain the increments in the displacement with respect to any kind of increment provided in the loads of the given system. So, you provide the load increment with respect to, say, either the values which are applied as a full, we can apply it at the one single step, or we can also go with this P1 value. If say this is the load of 10 units, I can go with the increment of 2, then the next increment of 4, and the next increment of, say, again 4 in the given system. So, based upon that, the user can apply the loads on a particular increment on the given system, which are defined by the user itself. So, these values of the dp1 and dp2 are known to us, and based upon this equation, the user will get to know that the value of the displacement increments which will be defined for the 0th iteration in the given system. Once these values are obtained, we will define them as the first value of the given system, say the updated values of the displacement, which are u of 3 and v of 3. These are obtained by considering the initial values, which were of course 0, and adding the new values in the given system, which are the incremented values of the given system. Now, once we get the value of the u3 and v3 in the given system, we again update the values of S1 and S2. And to evaluate the values of S1 and S2, I think we have already defined that very simplistic procedure where we write the S equal to A transpose, we define P is equal to A transpose S in the given system. So, once we have got the values of S1 and S2 by simply updating the member component of the displacements, we can also calculate the member forces which are active at the each nodes of the given system. So, what does it mean? That once we have obtained the values of the forces which are active in the direction of P1 and P2 from this updated value of the given system, we will realize that the net sum of the value of the forces which is coming in the direction of P1 and P2 or the incremented values are not same as the actual increment which we applied at the beginning. And that is what we can also do in a different manner. We can come up with the idea that calculate the F1 and F2, the new forces in the given system, by substituting this new value of the stiffness which has been obtained with respect to the updated S1 and S2 and multiply that with respect to the defined displacements u3 and v3 with respect to the first iteration in the given system. Now, this value will not come out as same as the initially defined dp1 and dp2 values of the given system. So, once we get these two values, we get the differences between the initially defined values and the new values of the given system, and this difference, if it is less than the tolerance value, we stop with the iterations. If it is not less than the tolerance value, we go with the next iteration in the given system. So, this is a very similar idea which we did in the Newton-Raphson scheme. Only thing, rather than taking it as a single variable value, now we have gone with a system in which there are more than 1 degrees of freedom available. So, this tolerance can either be done with respect to the value of this residue part, or it can also be done on the change in the displacement values which are being defined for each of the iteration step, and any of it once reached, we can stop with the given simulation, or we can stop with the given algorithm at that point, and that is the overall solution which we obtain for the given problem. So, with this part we have now covered the general description of the method which can include the geometrical stiffness in the given system and do the full scale analysis for the multi degree of freedom using the Newton-Raphson scheme. Now, once we are done with this part, we will briefly move ahead with the idea of the buckling in the given system, so that we can conclude the discussions on the geometrical stiffness of the geometrical nonlinearity of the given system. With this, we stop over here. Thank you everyone.